Beneath the surface of our everyday lives lies a hidden world, one that transforms the raw elements of the earth into the essential compounds that fuel our society. This is the world of chemical manufacturing, where science meets industry and where innovation shapes the materials that surround us. From the plastics in our phones to the medicines that heal us, chemical manufacturing is the beating heart of modern civilization. To truly appreciate its impact, we must journey back to the very beginning, to the origins where it all starts. Chapter 1: The Origins, Sourcing the Elements. Long before a chemical plant hums to life, the story begins with the earth itself. The elements needed for chemical manufacturing are not conjured from thin air. They are painstakingly sourced from the environment, each with its own journey from extraction to refinement. Petroleum, the lifeblood of countless industries, is drawn from deep within the Earth's crust. Ancient organic matter, compressed and transformed over millions of years, is now tapped by towering rigs that dot landscapes and ocean floors alike. Through a complex network of pipelines, this crude oil travels to refineries, where it is separated into its usable components: naphtha, kerosene, diesel, and more, each destined for its own chemical destiny. Minerals, too, are vital. Vast open-pit mines and subterranean tunnels yield ores such as bauxite for aluminum, phosphate rock for fertilizers, and lithium for batteries. These minerals are crushed, washed, and chemically treated to extract their valuable constituents. The journey from rock to refined chemical is a marvel of engineering and ingenuity. Gases play their part as well. Natural gas, primarily methane, is piped from underground reservoirs and purified to remove impurities. Other gases, like nitrogen from the air or chlorine from salt, are isolated through processes that separate, purify, and store them for later use. All of these raw materials, liquids, solids, and gases, converge at the gates of the chemical plant. Here they are stored in massive tanks and silos, queued up for transformation. Pipelines, conveyor belts, and automated systems direct the flow, ensuring that each input arrives in the right place at the right time. This orchestration of resources is the starting point for all chemical manufacturing, the foundation upon which the entire process is built. Chapter 2: The Reaction Core, where chemistry happens. Within the heart of the chemical plant lies its most dynamic and mysterious space, the reactor hall. Here, the raw materials undergo their most profound change, as molecular bonds are broken and reformed in a controlled dance of atoms. This is the reaction core, where chemistry truly happens. Industrial chemical reactors come in many forms, each tailored to the process at hand. Batch reactors resemble enormous mixing vats, where ingredients are loaded, reacted, and then emptied before the next batch begins. They offer flexibility and are commonly used for specialty chemicals, pharmaceuticals, and products where precision is paramount. Continuous reactors, by contrast, operate like well-oiled machines. Raw materials flow in at one end, products emerge at the other, and the chemistry never stops. Such reactors are the backbone of large-scale production, capable of churning out thousands of tons of product every day. Inside the reactor, conditions are tightly controlled to coax the desired reaction along. Temperature is carefully regulated. Too cold and the reaction stalls, too hot and dangerous side reactions may occur. Immense heaters and coolers work in concert, keeping the process in the sweet spot. Pressure is another crucial variable. Some reactions require high pressures, pushing molecules together to increase their chances of interacting. Others proceed best at atmospheric or even reduced pressures. Massive compressors, pumps, and valves ensure that every vessel operates within safe and effective limits. Catalysts, those unsung heroes of chemistry, are often introduced to speed up reactions without being consumed. These might be finely tuned powders, complex metals, or even custom-designed enzymes, each chosen for its ability to lower energy barriers and drive efficiency. But with power comes risk. The volatile nature of many reactions demands robust safety systems. Sensors constantly monitor temperature, pressure, and gas concentrations. If anything strays from normal, automatic shutdowns and relief valves leap into action. Fire suppression systems and blast walls stand guard against the unthinkable, while teams of engineers vigilantly oversee every step. It is here, in the controlled chaos of the reactor core, that raw materials are transformed into the building blocks of modern life: acids, plastics, fertilizers, medicines, and countless others. The mastery of this space is what makes chemical manufacturing possible. Chapter 3: Purification and Perfection. Emerging from the reactor, the journey is far from over. The products are rarely pure. Instead, they are tangled mixtures of desired compounds, leftover reactants, and unwanted byproducts. The next challenge is to separate, purify, and perfect these substances, elevating them from crude mixtures to high-value materials. Distillation towers rise like modern-day obelisks, their interiors a labyrinth of trays and packing. Here, mixtures are heated, and their components separated based on differences in boiling points. Lighter fractions rise to the top, while heavier ones sink, allowing for precise collection of each product. This technique, so simple in concept, is the linchpin of refining crude oils and producing solvents, fuels, and more. Filtration comes next for many products, removing solids from liquids or gases. Giant filter presses squeeze slurries while membranes with microscopic pores separate particles with astonishing precision. These filters ensure that only the purest material moves forward. Crystallization is often used for substances like pharmaceuticals, where purity is paramount. Solutions are cooled or evaporated, coaxing the product to form pure, solid crystals. These are then separated, washed, and dried, ready for their final use. In the modern chemical plant, automation and artificial intelligence are revolutionizing these processes. Sensors and cameras monitor every stage, while AI-driven control systems make real-time adjustments to maintain optimal conditions. Quality control labs, staffed by skilled analysts, use spectroscopy, chromatography, and other advanced techniques to verify purity down to parts per billion. Purity is not just a technical requirement, it is a matter of trust and safety. For medicines, even trace impurities can have profound effects. For electronic materials, a single contaminant can ruin an entire batch. Ensuring perfection is both a science and an art, blending cutting-edge technology with the expertise of generations. Chapter 4: Green Chemistry and the Future. As the world awakens to the consequences of industrialization, the chemical industry faces a new imperative: to create not just powerful products, but sustainable processes. This is the frontier of green chemistry, where innovation is harnessed to protect the planet. Traditional chemical manufacturing can be resource-intensive and polluting, generating waste, emissions, and hazardous byproducts. Today, scientists and engineers are reimagining every step, seeking to minimize impact and maximize efficiency. Sustainable manufacturing processes begin with the choice of raw materials. Whenever possible, renewable resources are favored. Plant-based feedstocks instead of petroleum, for example, or minerals sourced from environmentally responsible mines. Energy efficiency is paramount, with heat exchangers, insulation, and process integration reducing the need for fossil fuels. Biotechnology is playing a transformative role. Microbes and enzymes, engineered to perform specific reactions, can synthesize chemicals with far less energy and fewer toxic byproducts. Fermentation tanks, once the domain of breweries, now produce everything from biodegradable plastics to life-saving drugs. These biological processes often operate at mild temperatures and pressures, further reducing their environmental footprint. Circular chemistry is another groundbreaking approach. Instead of discarding chemical byproducts as waste, innovative plants capture, recycle, and reuse them. Carbon dioxide, once vented as a greenhouse gas, can be captured and converted into fuels or building materials. Solvents are recovered and purified for reuse, slashing the need for fresh inputs. The quest for sustainability extends beyond the plant itself. Companies are designing products with their entire life cycle in mind, making plastics that biodegrade, developing chemicals that break down safely, and creating processes that minimize water use and toxic emissions. Ultimately, the promise of green chemistry is a world where human progress and environmental stewardship go hand in hand. It is a vision of factories powered by renewable energy, producing materials that enrich our lives without depleting our planet. As we leave behind the towering pipes and humming machinery of the chemical plant, we are reminded of the profound impact this hidden world has on our daily lives. From the extraction of raw elements to the mastery of molecular transformations, from the pursuit of purity to the promise of sustainability, chemical manufacturing is a story of ingenuity, responsibility, and hope. It is a story that continues to unfold as scientists and engineers push the boundaries of what is possible, shaping a future where chemistry not only powers the world, but protects it as well. And though much of this world remains unseen, its influence is everywhere, in the products we use, the food we eat, the medicines that heal us, and the innovations that will define generations to come. Subscribe for more videos.